This is an autonomous materials lab. Its job is to discover a safe, lead-free perovskite for solar cells on robots and instruments a lab already owns. The hard part is not the chemistry. It is doing it in a handful of experiments instead of thousands, refusing the ones that are physically impossible before they burn reagents, and proving every decision afterward. Before the run, the panel that explains the mechanism. The goal is a single material that clears 3 windows at once. A bandgap between 1.2 and 1.5 electron volts for efficient absorption. Phase stability at or above 0.7 so it survives real conditions. And a decomposition point at or above 250 degrees Celsius for durability. All of it lead-free. It runs a closed design, make, test, analyze loop. A Gaussian-process surrogate with target-directed acquisition proposes the next candidate. A deterministic digital twin gates it on real physics. Survivors are synthesized and characterized, and every result feeds back so the next proposal is smarter. Agents advise, code decides. Every autonomous decision is written to an append-only, hash-chained ALCOA plus log. The tamper-evident record a regulated lab must file. And the run itself is an honest, physically motivated simulation, grounded in real perovskite chemistry, not a claim about a material anyone actually made. Now the campaign. One click starts an autonomous search that will stream over the next half-minute. The pipeline runs left to right. Propose a candidate, gate it, synthesize, measure, learn. The very first proposals never reach the robot. The gate stage lights amber and rejects them because most of the composition space is chemically doomed. The search is under live control. It can be paused at any moment, holding the stream, to inspect exactly what the loop is doing. Resumed, the search keeps proposing, gating and synthesizing. Each feasible candidate that survives the gate is synthesized and lands on the discovery map, bandgap across, phase stability up, and color showing decomposition temperature. The dashed box is the target spec, and the loop steers points into it rather than screening at random. The live feed carries every decision as it happens. Amber rows marked blocked are candidates the digital twin refused before synthesis. Teal rows are materials actually made and measured. Blocked never means an error. It means waste that was prevented. The loop keeps converging until the spec status flips. Target reached. A lead-free material inside every one of the 3 target windows. It got there in 75 experiments. A random screen on the identical hidden objective would expect roughly 1,500, so this is 19.9 times fewer experiments to the first spec meeting material. That multiple is this benchmark's number on a synthetic objective, not an open-world guarantee. The durable value is on the next tiles. Across the run, 38 infeasible syntheses were blocked before they ran, preventing $4,419 of reagent and 90 robot hours of wasted time, with 0 infeasible experiments ever executed. The discovered material is a lead-free tin-germanium halide perovskite, with a bandgap of 1.43 electron volts, a stability score of 0.74, and decomposition around 250 degrees. Opening it shows the measured properties against the target. Green checkmarks confirm all 3 objectives are inside their window at once. That is what promotion to best candidate means. Every spec met together, not one at a time. Any single decision opens the same way. The winning run, experiment 75, reads in spec on all 3 axes and carries its own hash-chained ALCOA plus receipt, the record that makes the result auditable later. The other half of the story is what never ran. The blocked panel counts 38 infeasible candidates caught by the digital twin, the same $4,400 and 90 hours saved, with the most recent violation named. The full list shows everyone. These were rejected on physics alone. Charge neutrality, the Goldschmidt tolerance window, tin oxidation hazard. No reagent and no robot time was ever spent on any of them. One card in detail. This candidate was blocked for a tin-2 oxidation hazard at process humidity. Tin-2 oxidizes in humid air, so the synthesis was doomed. The twin flagged it, named the rule, and recorded the reagent and robot hours it saved by refusing to run it. Stepping back to the finished map, an early scatter of dark points, then a dense cluster steered into the target box, and the bright white dot marking the best material found. The search visibly learned its way to spec. Now the part that makes any of this defensible. The provenance panel holds 113 records, one for every synthesis and every block, each cryptographically chained to the one before. This is the evidence a regulator under the FDA and EMA guidance requires: attributable, contemporaneous, original. It exports as a full report. Every autonomous step is a row. Its timestamp, whether it was a propose and synthesize or a block, the candidate, the gate verdict and any violated rule, and the chained hash. The banner at the top confirms the chain is intact and tamper-evident. Back in the console, the same panel offers a tamper test. It edits a single record deep in the log. Instantly the chain breaks at that record, and the panel reports exactly where. The filed audit is provably altered. That is the point. Trust in a self-driving lab cannot rest on a model's own word. It rests on evidence that cannot be quietly changed. 75 experiments to a lead-free target, every doomed synthesis stopped before it ran, and every decision provable after the fact. The brain, the safety gate, and the provenance layer, on hardware a lab already has. From Veriprajna, building true intelligence.